So, again, we talked about how we can make a molecule or an atom, we can turn it into an ion by either adding or removing electrons. If we add electrons, of course, we're adding some negative charge. If we remove electrons, we're removing negative charge, giving us a positive atom. We talked Friday about how we have some special names for these atoms: positive ions called cations and negative ions called anions. One thing that I wanted to bring up and just re-emphasize, right? To make a positive ion, if we add positive charge, what subatomic particle has a positive charge?
Protons.
Protons, absolutely. And so if we add a positive charge, we'd have to add a proton, right? And if we add a proton, what are we changing?
Change the element.
Absolutely, we're changing the element. We're changing that atomic number. And so here, we're changing that atomic number. And so we change the element. So we cannot make an ion by adding or removing protons. We can only make ions by adding and removing electrons. What's it called if we add and remove neutrons? Anybody remember that term?
It makes it an isotope.
Isotope, absolutely, isotope. And again, we'll deal more with isotopes in our lab on Thursday. Okay, so moving on, if we look at the periodic table, hopefully this is big enough that you can see it on your screen. But if we look at the periodic table, there are some trends that we see in these common ions. Let me tell you what I'm going to do. I'm going to jump out of this slideshow just a second and try to make this image just a little bit bigger. So hopefully it's a little easier to see on your screen. There we go. All right, so hopefully that's a little bit bigger for you. Let me share my screen again. All right. So looking at this periodic table, it shows some common elements. Again, remember, this is our standard periodic table from the textbook. So everything that's green is metal, everything that's blue is non-metal, and then these sort of purpley ones are metalloids. If we look at this first group, group 1, right, they all have a single plus charge. Right? If we look at this second group, group 2, they all have a 2 plus charge. Right? Maybe we're noticing some trends. But we come up here to group 6, and group 6, that's a +2 and a +3 on chromium. Group 7, a +2 and a +3 on manganese. Group 8, a +2 and a +3 on iron. And so these really don't fit any trend. So I'm going to jump over here. And if we look at this row, we have 3+, right? Remember, noble gases, the reason they're noble is because they don't really interact with anything. So let me just write noble gases here. But in this row, they're all -1. In this row, they're all -2. In this, sorry, I said row. These columns, -1, -2. This column, -3. It turns out that the periodic table is a great tool at helping us predict what the ion charge is going to be, especially if it's from those main groups. Remember, we call those main groups the taller columns in the periodic table. Those are our main group elements. And so if it's in the first group, it's going to be a +1. If it's in the second group, it's going to be a +2. If it's in this 13th group here, the third group of the main block elements, it's going to be a +3. That's where aluminum is. Right? It turns out that this is true because of the number of valence electrons. We have not gotten to really talking about what valence electrons are, but it's the outermost set of electrons in any element. And it turns out that that's what a lot of these periodic relationships, periodic properties have to do with, is those valence electrons. And so all the elements that are in group 1 have one valence electron. It's real easy for them to lose that one electron and become a positive ion. All the elements in group 2 have two valence electrons. It's real easy for them to lose two valence electrons and become 2+ ions. If we shift over to the halogens on the far side of the periodic table, those all have 7 valence electrons. Most elements want 8 valence electrons, and so it's easier for fluorine, chlorine, bromine, iodine to gain 1 electron than it is to lose all 7 of those valence electrons. So they tend to gain an electron so they can have those 8 electrons to complete what we call their valence shell. Same is true for oxygen, easier to gain 2 electrons than it is to lose 6 electrons. And so the position in the periodic table helps us determine whether or not they're going to gain or lose electrons. And if you'll notice, all of our non-metals here form negative ions, and all of our metals form positive ions. Part of the reason these metalloids are classified as metalloids are because sometimes they form positive ions, sometimes they form negative ions. There's no clear distinction there for those. Okay, we will come back and talk about these transition metal ions here when we talk about some naming conventions on Friday or Monday of next week. Okay. Any questions about those main group ions and sort of how we come up with the charge on those ions for the main group elements? All right. Hearing none, let's move on. When we look at formulas, we can think about formulas in a couple of different ways. Either a molecular formula, or an empirical formula. When we talk about a molecular formula, this is sort of as exact as we can be as scientists, right? And so this shows the exact number of each element, of atoms of each element. In the smallest unit of a substance. Okay, so we're talking about a single molecule or a single ion pair or something like that. The smallest possible unit of a substance, we're going to give exactly the number of atoms of each element in that unit, right? So if we talk about 1 molecule of water, of course we're going to write H2O, sorry. If we talk about 1 molecule of glucose, it's going to be C6H12O6, right? And so this gives us the exact number of each element, the exact number of atoms of each element in that unit, right? An empirical formula, on the other hand, is kind of a shorthand. It helps us classify things into families. And so this gives the lowest whole number ratio of atoms in a substance. Okay. And so since I mentioned water earlier, let's go ahead and think about water. The molecular formula for water is H2O. Can I simplify that and keep whole numbers? No, right? I can't clean that up any. So H2O stays H2O. I also mentioned sugar. Glucose is C6H12O6. Can I simplify that at all? Absolutely. What do I have to divide by?
6.
3.
6.
Oh, 6, yeah.
3 would work too, but it won't give me to the lowest ratio. If I divide by 6, I just get CH2O.
Ignore me. I just didn't get any sleep last night.
That's all right. Just sort of as a side note here, now you can see why sugars fall into the class of molecules known as carbohydrates, right? It's a carbon with a water molecule, so it's a carbohydrate as its empirical formula. The oxygen we breathe is O2, right? Remember, oxygen is one of those diatomic elements. But the empirical formula for O2 would just be O, right? That's kind of a weird one, but I just wanted you to see what it would look like for a single element, right? There's also some funny poisonous compounds of nitrogen. So C2H4, sorry, into H4. We can reduce that. We can divide both of those by 2 and just get NH2. Right? And so this empirical and molecular formula, sometimes it's helpful, sometimes it's not. It turns out that it's more helpful when we're dealing with ionic compounds than when we're dealing with molecular compounds. Now, we haven't talked a whole lot about the difference between those two, but ionic compounds are when we take 2 different ions, a positive and a negative ion, and form a compound due to the fact that those 2 are going to be attracted to one another. Molecular compounds are compounds that are held together by covalent bonds, which is where electrons are shared. Again, we'll get more into that as we talk about naming. But for molecules, we want to know exactly how many of each ion, of each element, sorry, are in that compound. And so when we talk about molecular covalent compounds, we'll usually give the molecular formula. When we talk about ionic compounds, we will usually give the empirical formula. Okay. All right, so let's see. All right, so here is a molecule of methylamine. Okay, just as a side note, this nitrogen here with 2 hydrogens, this is an amine. If you move on to organic chemistry, you'll see lots of amine kind of compounds. But let's write the molecular formula for methylamine based on this model, right? So we have some carbons, we have some nitrogens, and we have some hydrogens. How many carbons do we have?
1.
Just 1. How many nitrogens do we have?
1.
Just 1. And how many hydrogens?
5.
5. There's several ways that you can write this, and I want to give you as much freedom as possible. But generally speaking, when we write organic compounds or molecular compounds, if they have carbon and hydrogen, those 2 come first. So we'll have CH5N. This is the way that you will probably see methylamine written out. Right? There's another way that's not quite as compact, but that tells us a little bit more information, right? If we look at this compound, we see that there's that amine group that I already circled, and then we have this, well, it must be the methyl part of it, if this is methylamine, right? So we have methyl and we have amine. We could write this as CH3NH2, right? Split those hydrogens up. It tells us a little bit more information about exactly where those 5 hydrogens are bonded. So either of these answers is acceptable, right? Both of these are fine. Notice that I left out the 1s on the carbon and the nitrogen. That's because it's a little redundant, right? If we have a C there, we know we have to have at least 1. And if we have more than 1, then we put what that number is. But if it's just 1, we'll leave off that subscript 1. Okay. All right. One more example, empirical formula for these molecules. Acetylene, C2H2. Who's got a idea what that empirical formula might be?
CH.
Just CH, absolutely. C6H12O6, we already did that one. CH2O. Right. Nitrous oxide is laughing gas. What's the empirical formula for nitrous oxide?
N2O.
N2O. That's kind of like H2O, right? The empirical and the molecular formula are exactly the same. So sometimes we can simplify, sometimes we can't. Okay. So that's molecular versus empirical formulas. Okay. So getting into some ionic compounds. Right? When we form ionic compounds, well, you can imagine that they're going to have some ions in them. And so these are formed from the combination of positive and negative ions. The forces that hold charge together are called electrostatic forces. You may see that term in some ALEKS questions. Right, and so these ions, these plus and minus charges, are held together by electrostatic forces. Okay. Again, for ionic compounds, we're going to give that empirical formula. And the reason we do that is ionic compounds are usually these huge aggregations of ions. Instead of a single Na plus and a single Cl minus, when you see a grain of salt, it is billions upon billions of atoms of sodium, ions of sodium, and ions of chlorine in there. One of the keys, though, is that as we build this larger and larger crystal, the net charge, right, so the overall charge must be 0. Okay. So again, our most famous ionic compound is sodium chloride, right? We know that that's made up of Na plus and Cl minus. And they go together in a ratio where there's an equal number of positive sodium ions and negative chlorine ions. Right? There's a couple ways of looking at this. All the way on the right, of course, you recognize a salt crystal. But if we look at the one in the middle, this is sometimes called a space filling model. And then the one on the left is a ball and stick model, where you can sort of see the connections maybe a little bit better. It turns out that the larger ones are the chlorine ions, sorry, and the smaller ones are the sodium ions. And so they're held together in this crystal arrangement. So there's an even number of chlorine and sodium ions. When we think about sort of bringing ions together to form compounds, it's not always nice and easy where there's one sodium for every chlorine, and so it's a 1-to-1 ratio. A lot of times we have to think about bringing together multiply charged ions. That's why we took a look at the common ions in the periodic table earlier, right? I can remember this first column is always going to be just a single plus charge. The second column is always going to be 2 plus charges. We jump over here, aluminum is 3 plus, nitrogen 3 minus, because it's easier for him to gain 3 electrons than lose 5 electrons. This column here 2 minus, and this column here 1 minus. Right? Ionic compounds are made of these metals and nonmetals, these reactive species, and so you'll always have a metal being the positive ion and a nonmetal being the negative ion. And so metals are always what? If they're positive ions, what's our special name for positive ions?
Cations.
Cations. And our nonmetals are always
Anions.
anions. Absolutely. Okay. So let's do a little bit of practice here. Before we do a bit of practice, polyatomic ions. When we look at this list of polyatomic ions, these you need to know, right? For not the first quest, but for the second quest, you'll need to know this list of polyatomic ions, and for all of the quests after that. Once we get into naming, you'll be responsible for being able to name any chemical compound that we come across. But sort of what I tell you is that you won't have to know more than this set of polyatomic ions, because we pretty much have to memorize these names. I don't want to give you too big of a list, and so this is 15 polyatomics. Let's see, is that right? No, this is 19 polyatomics. So it's kind of a big list, but it's we'll use them a lot, and so hopefully memorizing them won't be too much of an issue, right? Again, polyatomic mini atoms, right? These are just sets of atoms that are held together with those covalent bonds, those electron sharing forces. But once they're held together, once they're bonded together, they have usually extra electrons. That's why they're negative ions, most of them, except this guy up here, ammonium, NH4+. And so this PowerPoint's on Moodle, right? And so you don't have to worry about copying things down from this screen. But I do want you to make sure that you know these by Quest 2. Okay. All right. Just for a little bit of quick practice here, if we look at the nitrate ion, I hope this is big enough. Can you all see that that's NO3 with a 1- charge, right? And so if I had sodium plus and NO3, then I would make a compound known as sodium nitrate. I don't want to get too deep into naming today, but that one's easy enough to do, just sodium and then the name of the ion, nitrate. What if I wanted to do magnesium nitrate? If you look on that previous slide, what's the charge of magnesium? Which group is magnesium in?
2.
2A.
Yeah, he's in 2A, so he has a 2+ charge. And so in order to get those charges balanced, how many nitrate ions do I need?
2.
2.
Two.
Absolutely. And so if I have a magnesium and 2 nitrates, we're going to form magnesium nitrate, NO3. In order to indicate that I have 2 nitrate units, I don't just put a 2 there, because that looks like it's 32 oxygens, right? That's way too many. I also can't just put a 2 out here, because we don't need numbers in the middle of our chemical formula. So the best way to do it is to put some parentheses around it, and then use our subscripts, right? So we have a magnesium, and then those parentheses tell us that we have 2 nitrate ions together with that magnesium. When we write our ionic species, we're always going to put the cation first, right? Always going to put the cation first, and then the note that I'll make down here, indicate multiple polyatomics with parentheses. Okay, so always put the cation first, and if we need more than one polyatomic ion, always indicate that in parentheses with the subscript. Okay. All right. Now, looking at some ionic compounds. Here we have Al2O3. Right? If we're given this compound, we should be able to break apart what the species are. Right? So here we have aluminum, and here we have oxygen. Do we know what aluminum's charge normally is based on its position in the periodic table?
+3.
That's right, absolutely. Okay. So if there are 3 positive charges on the aluminum, and the aluminum has, and there are 2 aluminum ions, what's the total amount of positive charge?
6.
That's right. Well, I've got 6 plus charges because I've got 2 aluminums with 3 positive charges each, right? And so I need to have 6 negative charges so things balance out. I've got 3 oxygens, so that must mean each oxygen is a 2 minus. And of course that follows with what we know from our periodic table. Oxygen has a 2 negative charge, right? We can do the same for calcium and bromine. Calcium, he's 2 plus, there's only 1 of him. Bromine is 1 minus, but there's 2 of him. And so they cancel each other out as long as we have 2 bromines. What if I wanted to have a compound like lithium and phosphate? If you need to sort of fiddle around in your version of the PowerPoint slides to figure out the charge of those 2, what's the charge on lithium?
2. 1.
He's in that first group. He's in the first column. And so lithium
Plus
is
1.
1. Yep. And how about phosphate from our polyatomic sheet?
3 minus.
Minus 3.
Yep, absolutely. And so how many lithium ions do I need for every phosphate?
3.
I need 3, right? And so I end up with 3 lithiums. Again, I represent that by a subscript with 1 phosphate ion. Because I've just got 1, I don't need the parentheses, right? If I had more than 1, then I would need some parentheses. A shortcut that you can use is you can take this charge here, and that's the number for lithium. You can take this charge here, and that's the number for phosphate, right? I need 3 lithiums and 1 phosphate, and that's the formula we came up with. Okay. All right, how about something like calcium and sulfate, SO4? What's the formula for calcium? Oh, sorry, not the formula, the charge for calcium.
Plus 2.
Plus 2, and how about sulfate?
-2.
Minus 2.
Yeah. And so if I use that charge rule, then I'll end up with Ca2SO42. Right. But remember, we always want to write our ionic compounds in their empirical formulas. And so that we're going to just take all those 2's away, CaSO4. Okay? And again, we don't need the parentheses as long as we only have 1 of a particular polyatomic.
Yeah, I got a question.
Go ahead, Michael.
You know how you put the SO4 in parentheses and a 2?
Yes, sir.
Would you be wrong if you just put an 8 there?
If I put an 8?
Yes, sir.
Yeah. So because there are 8 oxygens, but there's also 2 sulfurs, right? And so we write this as SO4 2 to show that it's 2 sulfate groups, rather than writing it this way as S2O8, because S2O8 could be something else, right? It could be a separate kind of group. As a matter of fact, I think that's called persulfate, S2O8. And so we don't want to distribute that 2 across, because we just want to make sure that we sort of recognize that it's 2 sulfate groups rather than trying to simplify it.
So how come if they're already balanced, like the 2 plus and the 2 minus, how come you have to go and put another subscript of 2?
So you do not have to do that. I was just showing that you can use that little charge switch method that I showed up here in the lithium phosphate. You can use that all the time as long as you remember to reduce it to the empirical formula if possible. If you are smart enough to recognize that one calcium and one sulfate will go together and match, then you can just write CaSO4, absolutely. Please do that. And I hope we all get to the point where we're good enough to do that. But this charge switch method is sort of just an easy shortcut if you're having issues figuring out how many of each one you need.
Okay, thank you.
Yep. Okay. All right. So how about if we were doing magnesium and nitrogen? Magnesium is a 2+, nitrogen is a 3-. What's my formula going to be?
Mg3 N2.
Absolutely. Mg3 N2. Again, that charge switch method works well. Or we can go, okay, what's my lowest common multiple of this 2+ and 3-, right? Maybe bring back some algebra 2, lowest common multiple stuff. But you'll end up with, you need 6 overall charges. So 6 positive charges means 3 magnesiums, and 6 negative charges means 2 nitrogens. Okay? Mg32. Any questions about how we come up with ionic formulas, about how we know the charge of an element based on its position in the periodic table, anything like that?
How could you, could it be into Mg3? Like, why does the magnesium come first?
Yeah, so just one of the rules that we have when we write formulas, especially for ionic formulas, we always put the cation first. We will always put that positive ion out front. So for ionic compounds, we will always have the cation first. Okay.
Will we be able to use the charges on the periodic table for the quest?
So you'll have access to a periodic table. It won't have the charges there, but you'll know, of course, group 1 is +1, group 2 is +2. If you jump over to aluminum, that's +3, and then we switch to negatives. Halogens, -1, the group with oxygen, -2, the group with nitrogen, -3. Okay. And we'll have much more practice between now and Quest 2. Remember, Quest 2 is not this week, but next week. Okay. All right. So I don't want to get us too deep into nomenclature, but since we talked about ionic compounds, it makes sense to start speaking like we know what we're talking about in terms of names, right? And so for ionic compounds, right, this is going to be a metal cation and a non-metal anion. Okay. Remember that there is one positive cation that's polyatomic, right? NH4+. And so I say metal cation because that is almost always what it is. But remember that there is that ammonium cation that could be used here. But usually it's a metal cation with some non-metal anion. Right? Our rule for the non-metal is that we change the ending to IDE. Okay. And I'll put here in parentheses, this is not for polyatomics. For a polyatomic ion, we just use the name that's given. Okay. So like sulfates, we don't change that to sulfide. Sulfide's already something different. We leave it as sulfate. For the metal part, we do not change the name. And so we know this one pretty well. We've talked about it already, right? We know that Na is sodium. Cl is chlorine. We're going to change that chlorine to IDE, and so we get chloride. Okay. And so chloride will refer to Cl minus. It's always going to refer to the ion. What would be the name for BaCl2? Who knows your element names enough? What's Ba?
Barium.
Barium.
Barium, absolutely, barium. And then Cl2, is that different from Cl?
No, it would still
Not.
be barium chloride.
Yeah, barium chloride, absolutely. Things don't change. We just know we need 2 chlorides because barium's a +2, chloride's a -1. Based on the charges, we know we need 2 chlorides. The name doesn't change. How about if we had K2O? What's our element K?
Potassium.
Potassium.
Potassium. And so how do I make oxygen into an anion?
Add the IDE at
Yep,
the end.
and so it becomes
Oxide.
oxide. Absolutely. And so sort of, what you take off to add that IDE, there's no set rule. It's just kind of what sounds right? We're not going to make it oxide for oxygen or oxygen, right? We're going to make it oxide. And so we're going to take the ending off and add IDE. If we move into some polyatomics, if you need to go back and look up the name for that polyatomic, but this first part's just magnesium. And then what's that polyatomic called?
Hydroxide.
Hydroxide. I don't need to put anything to indicate that there's 2 of them, because if I know it's magnesium, I know it's 2+ based on the fact that it's in the group 2 in the periodic table. And if I know it's hydroxide, I know it's 1- because I've memorized those 19 polyatomic ions. And so I know that 2+ charges from magnesium need 2 negative charges from 2 different hydroxide ions to cancel out, to neutralize. And so I don't need to put anything about the fact that there's 2 hydroxides in the name for ionic compounds. And so I'll just make a quick little note here, right? We do not include numbers of ions in ionic naming. Okay? We do not include the numbers of any ions in ionic naming. Okay? All right. So those transition metals, remember I told you that for the main groups, it's easy to know what their charge is based on which group they're in the periodic table. For transition metals, it's a little bit funnier. It's hard for us to know what the charge is going to be. And so almost always, we have to be given a little bit of information about the compound, right? And so these transition metals can have multiple charges. So for example, iron can be iron 2+ or iron 3+. Both of those ions exist, and they behave very differently based on the number of charges. When we go to write out a name, so I'm going to stick with iron for our examples, and I'll just do chloride because we're familiar with that one already. So we could either have FeCl2 or FeCl3, right? If I have FeCl2, what's the charge on that iron?
+2.
2+.
Absolutely. So if it's FeCl2, then I know that there's 2 positive charges on that iron. The way that we indicate that is with Roman numerals. And so I'm going to write iron, and in parentheses, I'm going to put the charge on the iron. So it's iron 2 chloride. Right? Now, I'll tell you right now, students get tricked up with this because they want there to be 2 iron atoms, because it's iron 2, right? That 2 does not refer to the number of atoms, it refers to the charge on the metal. And so for this bottom one, where it's iron with 3 chlorines, what do you think the name is going to be? Iron
3.
3 chloride. Right? One of these is red and one of these is yellow. I can't remember off the top of my head which is which. But they do have different physical properties, different chemical properties. And so we use this naming scheme to separate out, to differentiate between what charge a particular transition metal has. Right? And so, you know, if you're given a name or given the formula, you should be able to figure out what the charge is based on what the negative ion is, right? And so let me give you one more. How about, how about this? MnSO4 3. Right? We don't know the charge on manganese. Manganese is right here in the periodic table, right? He doesn't have a set charge. He's a transition metal. But we know the charge on sulfates, right? Sulfate's one of our polyatomics. We've memorized our 19, and we know that sulfate has what charge?
2 minus.
-2.
-2, right? -2. And so if we know that he's -2, and there's 3 of him, what's the overall number of negative charges?
6.
6.
-6. And so I've got -6 overall. I've only got 1 manganese, and so this must be manganese 6 sulfate. Right? Manganese 6 sulfate. One more that gets a little tricky, and then I'll let you go. Ti3PO42. Titanium, he's one of our transition metals. He's right there. We don't know what his charge is, but we know phosphates. What's the charge on phosphates?
3 minus.
3 minus, and we've got 2 of them. And so we have a total of 6 negative. Does that mean that titanium is 6 plus? No, why not?
Because it has a substrate.
Because there's not just 1 titanium, there's 2, right? We've got 2 titanium ions to distribute that charge across. And so here we've got 2 times 3 negative charge. Here it's 3 times, well, it must be a 2 plus for those things to balance out, right? And so we've got titanium 2 phosphates. Okay. Any questions about that naming? We will do a lot more with naming in the weeks to come. I just wanted to, since we had seen some ionic compounds, I wanted us to get at least a little bit of naming snuck in here so we can sort of talk about them a little more fully. All right, I'm going to call that quits for today. A reminder that Wednesday's class is going to be mostly office hours. The waiting room will be open, and so it won't just be, you know, all 20 of you in here asking questions. I'll let you in out of the waiting room. You can ask a question. I might give you a problem to work on and put you back in the waiting room while I help somebody else, right? And so if you want to come Wednesday and ask some questions, by all means do that. I look forward to it. If Wednesday, if we run out of time on Wednesday and you want to meet at a different time, let me know. Or if you want to meet tomorrow morning before the Alex stuff is due, let me know and we can arrange a time tomorrow before 11. Okay. All right.
Sounds good.
Any questions before we head out today? Matthew?
I got one more. So if we've already completed the first unit of the Alex, we don't need to do anything, no need to notify, nothing like that.
Nope. Yeah, if you've already completed the intro units and sig part of Alex, then you are all done for Tuesday. You just need to make sure you're ready for the quest on Thursday.
All right, thank you.
Yep. Okay. All right. We all have a good afternoon.
Thank you so much.
You too, thanks.
Thank you.
Thank you.
you.
You too. Have a great day.